Let's come back to our original problem of expressing a function in this vector space of piecewise continuously differentiable functions on the interval from 0 to 2 pi, expressing such a function in terms of this basis that we found. And when I say in terms of this basis, what I mean is as a potentially infinite linear combination of these basis elements. So because this does form a basis, caveat quotes around basis there because we have to use possibly infinite linear combinations, but because this is a basis, we can write such a function as some multiple of 1, which we'll call this coefficient a sub 0, I guess, times 1 plus, and then we might need infinitely many of these sines and cosines, so we'll have to do a sum from n equals 1 to infinity, but we'll have a coefficient times, a coefficient, we'll call it a sub n, times one of the sine functions, so sine nx, plus another coefficient, which we'll call b sub n, times cosine nx. Right? So this, and what we're trying to do here is find out what are these coefficients. How can we find the components of any given function relative to this basis? Well, because this is an orthogonal basis, we have a shortcut, right? We know in finite dimensional vector spaces anyway, if you have an orthonormal basis, say beta 1 through beta n for some vector space, then any vector is equal to, let's say an orthogonal basis. We could use an orthonormal basis, but because this basis is orthogonal but not orthonormal, I want to review the orthogonal basis version. So in the finite dimensional case, this would be v inner product with your first basis element divided by the norm squared of your first basis element times the first basis element, and then the same all the way down to the last basis element. So v inner product with your last basis element divided by the norm of your last basis element squared times your last basis element. Okay. Well, exactly the same thing goes for this case because we have one of these bases, and again quotes around bases. So to compute all of these coefficients, all we need to do is work out what is the inner product of any particular function that we're interested in with each of these basis elements. Of course, there are infinitely many basis elements, so there are sort of infinitely many inner products to work out. But of course, the basis elements come in sort of three flavors. There's the constant one, there's the sine one, and then there's the cosine one. So really, it'll usually come down to just doing these three different cases individually. Incidentally, writing a function as a linear combination in this way, this linear combination is called the Fourier series for f, for the function f. So if you get into a field where there's a lot of dealing with signals like signal processing and image processing, lots of things like that work very heavily with Fourier series because they decompose functions based on the frequency components hiding inside of that function. So let's work out an example of finding a Fourier series. So let's use this function. F of x is 2 times sine 2x minus 3 cosine 5x. Now, of course, this particular function I have written down as its Fourier series already. So really, all we're doing for this particular example is just checking that that the process that we have of computing a Fourier series by term by term by computing these inner products really does work. We'll look at more complicated examples later. So to start out with, remember what we need to do is calculate the inner product of this function with each of the basis elements, all of the constant function 1, and then all of the sines and cosines. So let's look at one inner product with f. Okay, this is the integral from 0 to 2 pi of 1 times 2 sine 2x minus 3 cosine 5x. And then, for each one of these integrals, we're going to have to do some messy stuff to compute what this integral is. For this particular integral, since this function is built out of sines and cosines, right, we can sort of tear things apart so it looks like this: 2 times integral from 0 to 2 pi of sine 2x, right, dx, minus 3 times the integral from 0 to 2 pi of cosine of 5x dx. Okay, and both of these integrals turn out to be 0. So the one component of the Fourier series is 0. All right, now let's look at the rest of them. Well, we'll do one more example, and then we'll skip to a shortcut. So for another example, we might want to do take the inner product sine x and our function. Okay. So this is going to give us the coefficient for the, actually, we sort of know ahead of time that this one is going to be 0. So let's skip ahead to one of the ones that isn't 0. So how about sine 2x? Yeah, let's do this one. Okay, so this is the integral from 0 to 2 pi of sine of 2x times 2 sine 2x minus 3 cosine 5x. Okay, now just like when we computed the last inner product, we can distribute all this stuff and pull constants outside of the integrals. So 2 integral from 0 to 2 pi of sine 2x times another sine 2x minus dx minus 3 times integral of sine 2x times cosine 5x dx. Okay, so 2 times. Now, this integral, we actually already have worked out this integral, right? This is the inner product of sine 2x with itself, and we know that that's going to give us pi. Okay, and then minus 3 times, and here, this one is the inner product of sine 2x and cosine 5x, but that one we know is 0. Okay, so we get just 2 pi. All right, you can see by the same token, right, what this inner product is doing is just sort of pulling off the coefficient for the corresponding term, the corresponding trig term in this sum, but then also multiplying by a factor having to do with the magnitude or the norm of the basis element that we're working with. So, right, most of these inner products are going to be 0. The only other one that isn't going to be 0 is the inner product with cosine 5x. And we can run through the same thing here, but we're going to get minus 3 pi. Okay, so let's put these together to express our function in terms of its Fourier series. Right, so we know that this is going to be, we only need to write down the terms where the coefficient isn't 0, and of course there were only 2 of those. So there's the term with the inner product with sine 2x, and then we have to divide this by the square of the norm of 2x, and then multiply by 2x, okay, plus, and then the same thing but for the other non-zero term, which is the one coming from cosine 5x. f of x, and then divide by the square of the norm of cosine 5x times cosine 5x. Okay, but we worked out these inner products. This one up here is 2 pi. Okay, and then divide by the square of the norm. But remember, the norm of sine 2x was the square root of pi. Okay, times sine 2x plus, and then this inner product up here is minus 3 times pi. And down here, again, the norm of cosine 5x with this inner product is square root of pi again, times cosine 5x. And when we simplify all of this, of course, the pi's all simplifies, so we get 2 sine 2x minus 3 times cosine 5x. And, you know, this is the function that we started with, but the point of this example is just to see that taking all of these inner products and using this formula to express a function in terms of its Fourier series does give you a series that represents the function that you started with. So in this particular example, because we started with such a simple function that was already in its Fourier form, of course, since we started with the Fourier series, when we write the Fourier series, we just get another Fourier series, the same Fourier series. But this was just a simple example to see how it all works. Our next example will be a little more complicated.